All right, so biomolecules, again, molecules synthesized by living things. They are primarily composed of carbon, right, the element carbon, and they have other elements as well. So there's oxygen, hydrogen, nitrogen, there can even be sulfur, phosphorus, but the main ones are these four: carbon, hydrogen, oxygen, nitrogen, okay? And they form four basic biomolecules: carbs or carbohydrates, lipids or fats, proteins, and then nucleic acids, which make up our DNA. So today we'll talk a lot about the details of what distinguishes each of these biomolecules from each other. It's very important to understand that they're all made of the same atoms, so the way that they are organized or the way that they are made up uniquely sets them apart from each other. And that's that form follows function. You'll continue to see that precedent throughout this course. The way a thing looks dictates the way it behaves. Something is uniquely shaped, it has more of this than that, that's going to dictate it behaving in a certain way. And we'll see that with these molecules. Let's start out by talking about carbohydrates. So these are the main bulk of our food groups, to be honest, right? It's the bulk of what we eat, carbohydrates. They're composed of carbon, hydrogen, and oxygen. There are three main types of carbohydrates. There are monosaccharides. And monosaccharides are basically monomers of carbohydrates. So when you think about a monomer, what's a monomer? Right, so it's one sugar or one link in a chain of separate things. So a monomer here would be glucose. So it's a single carbohydrate on its own, not linked to another one. And then galactose is another example, and then fructose is another example as well. So these are examples of monosaccharides, which are single, simple sugars or carbohydrates. We get more complicated or more complex when we look at disaccharides and polysaccharides. Now, disaccharides have two sugars, as that prefix implies. So we have sucrose, which has glucose and fructose. And sucrose is what? Sugar, right? Table sugar. We have lactose, which happens to be galactose, and glucose, which is what? What's lactose? Where do we find it? In milk, right? It's milk sugar, correct. So these are examples of disaccharides. And again, all we have here is two monomers being covalently bound to one another, okay? The third example we have are polysaccharides, and these are much more complex carbohydrates. The example we're looking at here is the glycogen, and we can see this is made of several storage units of these monomers that we talked about first. So the example with glycogen is the storage of glucose. Where do we typically find glycogen? Or where do we typically see it? So if it's the storage form of glucose, where do we store away our energy reserves? What parts of the body? I think I'm hearing it. Did I hear liver? Is that what I heard? Yeah, so the liver is correct, as well as muscle, right? So liver and muscle are two areas that we see glucose being stored away as glycogen. All right. Let's talk about how these carbohydrates are synthesized and how they are metabolized or broken down. So in order to bind those two monomers that we talked about, they need to be linked by a covalent bond. And this process is called condensation. So condensation is that reaction of joining two monosaccharides or two monomers together, releasing water. And this is not exclusive to carbs. We'll see this with proteins as well, right? So linking those two monomers together, releasing water, and they'll be joined together in this saccharide, which is the bonded form of this molecule. All right, alternatively, hydrolysis is splitting of that larger saccharide into smaller components by inserting water into that molecule. Okay, so the addition of water splits that covalent bond, and we have our two monomers like what we started with. Okay, so understand these two reactions and the difference between them: condensation and hydrolysis. Any questions on carbohydrates? Any questions on carbohydrates? Okay, let's talk about lipids here. So lipids are another important part of our diet. Okay, they're my favorite macromolecule, right? They make food taste really great. I'm sure we can attest to that. They're composed mainly of hydrogen, carbon, and very little oxygen. This very little oxygen is an important part, bless you, an important part of their functionality. Okay, so lipids can be triglycerides, ketones, phospholipids, eicosanoids, steroids, and the unique principle about lipids is that they are nonpolar and they are hydrophobic. What does that mean? What does that nonpolar bit mean? When something's nonpolar, what does it mean? It's not charged, right? Or it's neutrally charged, right? There's not a lot of separation of charge around the molecule. And when we think about lipids, they don't have a lot of oxygen. And we know oxygen is an electron hog. It hates to share electrons. And so molecules with lots of oxygen have that instability. They have that separation of charge or that partial charge around the molecule because oxygen is trying to grab and sort of fight the other molecules for their electrons. With lipids, we don't see that because there's not lots of oxygen here. Any question? No? So there's not lots of oxygen here. And so we see very neutral charged molecules, right? Very steady with the charge or stable charge around these molecules. And so these molecules don't play nicely with the other molecules that are polar. So carbohydrates are polar, proteins are polar, nucleotides are polar, water is polar, right? There's that separation of charge. And so lipids sort of stand alone in this regard. They don't play nicely with water. And so that becomes a conundrum in the body. Why? We have to move lipids around and the body's made mostly of water. Okay, so we're going to talk a lot about how lipids have to sort of act differently to move around the body because of this makeup, this chemical makeup. Let's start by looking at triglycerides here. Triglycerides are made of a glycerol backbone, which is this component here. And this is a 3-carbon alcohol. And it's also attached to 3 what we call fatty acid tails, which are these extending parts here. And these are long carbon chain acids. So just carbons sticked onto one another, making that tail. And there are 3 of those attached to this one glycerol backbone, okay? Now, there can be lots and lots and lots of variation with triglycerides. And what we see is they can be fatty acid, they can be, saturated or unsaturated. Does anyone know what those two mean? Saturated versus unsaturated in terms of triglycerides. Sort of, not so much. But basically a saturated fatty acid has to do with how many double bonds are on that fatty acid. So for example, these are saturated, meaning that they cannot hold any more hydrogens, right? There are no double bonds along here. Whereas unsaturated fatty acids do have some double bonds. And so they could potentially have some more hydrogens come on there. They're not fully saturated. Okay, that's the difference between a saturated fatty acid and an unsaturated fatty acid. And we can also further see that among unsaturated fatty acids, they can be cis or trans. And cis or trans has to do with the direction that the hydrogens are facing. So if both hydrogens are on the same side or the same face of this double bond, it's going to be a cis meaning same, a cis fatty acid, whereas if they're on opposite or polar ends of this double bond, it's going to be a trans fatty acid. Now, I point this out to show or to illustrate that these very subtle differences, so the same molecule, essentially, the same atoms, carbon, hydrogen, oxygen, very slight differences. So for example, the difference between a cis and a trans fatty acid is just the direction of that hydrogen. And this can be the difference between a good fat and a bad fat. As we know, trans fatty acids are a little bit more unhealthy than cis fatty acids. And so the driving point here is that very small little differences in these molecules and their chemical makeup can determine big functional differences, like the difference between a good fat and a bad fat. And we see that very similar phenomenon with saturated and unsaturated fatty acids. The saturated fatty acids tend to be slightly unhealthier than the cis fatty acids. The cis fatty acids. All right, any questions on triglycerides? Major part of our diet, major part of our energy storage. Let's look at ketones, which is the second subgroup of lipids here. So ketones are usually seen in diabetics or persons that are on a low carbohydrate diet. I'm sure many of you have heard of the ketogenic diet or the ketosis diets. And basically you restrict your carbohydrates, which is the same physiological experience as if you are a type 1 diabetic. You limit the amount of glucose, or you limit the amounts of insulin spike that's happening in your body, and you shift your major metabolism from carbohydrates to fats. And so you start breaking down fats, and a breakdown product of these free fatty acids is ketones. Okay, so this is one of the end products of the breakdown of fatty acids. They're going to be converted into ketones by the liver and mobilized throughout your body. Now, this can become dangerous if there's a buildup of these ketones, right? In moderation, if you're on a ketogenic diet, it's not detrimental, but if there's buildup of those ketones, we can end up with ketoacidosis or ketosis, which is a life-threatening condition. Okay, and just to sort of tie this back to what we talked about on Friday, we said that very small fluctuations in pH could be life-threatening, and this is an example. These excess ketones are quite acidic, and they make the blood excess acidic, and this is where we can have life-threatening complications with ketoacidosis. We also see ketone breath or acetone breath with these persons or these patients. Basically, there's a metallic sensation in the mouth, or there's like a metallic-y odor, or this metallic-y acetone type breath. And that's because of the excess ketones in the blood, which is that acidic component that's coming out on the breath. Now, examples we have here, this is what a ketone looks like. So it's basically a carbon double bound to an oxygen, and then these R's represent some type of functional group. So there's lots of variability with what these functional groups can be. And to look at a specific example, which is acetoacetic acid, one type of ketone, this has a hydroxyl on this side and a methyl on that side. And again, this is just one type of ketone. So ketones have a carbon double bound to an oxygen, and then it can be some type of functional group at the end there.